Hey everyone, Mrs. Slauson. So we are looking at the Showcase of Learning 1 retake practice. And when you are finished with this, you do need to bring it back to me. We'll make sure that it's done. And then we'll get you set up for a time where you can retake that Showcase of Learning. So if you don't have this, this is in the same box where you found the video. You can also just put it on paper, but you did have access to a printout when you were in class. So hopefully you have that. All right. So at this point, I'm going to switch this so you won't see me anymore. So just a heads up on that. So I'm going to move out of this video. Here I go. And now you're just going to see the screen. So let's get started. All right, in our first one, we are looking at a table that shows the winning times for the women Olympic marathons. So in our original Showcase of Learning, it was for the men's, but now we're going to look at the women's. And so what we should be noticing is the same thing that we noticed on the last set, that our data is going down. And what's going to happen is, given this equation or this information here, we're going to write our linear equation of best fit. So what they do when they give you this is they give you the format of the equation they want you to use, this y equals ax plus b. And so I'll take the fact that they give me a, which is this number, this negative 2.52. I'm going to go to the nearest thousands. And they give me b. And so when I use that number, I will round that up to 566 at the end. But everything that I just highlighted is what's going to go into our equation. So it's just y equals, and then a is a negative 0.252. You put the x behind it, plus your b. The next thing we're going to ask is the R value. So the R value should not be confused with this R of G equals 1 plus or minus R. The R that's here is known as the correlation coefficient, and that's this number that I'm circling. And so I'm just going to write that down. Again, I'm just going to go to like 3 numbers. Whoops, sorry. Behind the decimal. So negative 0.662. So now we want to interpret this R number right here. So the first thing, it's negative, so that's going to take out option number 1, and it's going to take out option number 2. So it's either going to be 3 or 4. And when I look at R, I want R to be one of 2 numbers. I want it to be either a negative 1 or I want it to be 1. It just depends if it's positive or negative. So when I look at this, I definitely know it's negative because of the negative in front of the 0.662, but now I want to say, is it strong or weak? And when I compare this number, this negative 0.66 to this, that's pretty far off. So that would definitely not be strong. That would actually be more of a weak relationship. Okay? Now let's go to the describing of the different parts. So the first thing we're going to do is identify the y-intercept. So b is a number that's by itself. So that is that 149.566. And what that means is it's the beginning. It's always the beginning. And then what I do is, since it's a y-intercept, I go to my table and I realize that y is my race time in minutes. So it's the beginning race time. So when they started looking at this data, they're saying that the first person had an amount of about 149.566. Okay? Now we're going to identify the slope. And in this one, normally it's m, and m is married to x, but this time it's going to be an a. So that a value, this negative 0.252, is going to be my slope. And remember, slope is another word for average rate of change. So what we're looking at is, if you go to the top, remember what's changing is our race time, and our race time is going down. What this number is doing, this negative 2.52, is telling you how fast it's changing. So the race time is decreasing. And I know it's decreasing. I can see that in the table. I can see that because the number circled is a negative number. 0.252 minutes every year. Now, this seems awkward to us. What's 0.252 minutes? So if you really wanted to do that, let me just bring my calculator into the screen. You could find that out. You could take 0.2, whoops, it's not turned on. You could take, if it turns on, 0.252. And if you think of how many seconds are in a minute, that's 60 seconds. I could actually take that times 60. And what this is saying, it's actually the race time is going down by about 15 seconds every year. And that makes much more sense to us. But that's not how we were asked to answer it. So we'll just leave it the way it is. All right, let's move this camera out or calculator out and move to the next one. So what would you expect the winning time to be in the year 2017? And it says, remember, the table represents data since 1990. It actually doesn't say that up here, but that's what it means. So 2017 is how many years after 1990? And if you don't know, you can just take a calculator and take your 2017 and subtract your 1990. Otherwise, you can do that in your head, whichever you want to do, doesn't matter. So when I do that, we get 27 years, and that is the number that we're going to put into our equation. We're going to put it into this equation right here, the one that we wrote down. And so the way to show your work is to show me what you are typing in. So instead of X, I'll put 27. And then as far as I'm concerned, then you just go to your calculator and you type this in exactly as you see it. Okay? And I realized my decimal did not show up very well here. So if I bring the calculator back in, sorry, you can't see what you need to see. Then I'm just going to type that in. So I'm going to do negative 0.252. In parentheses, I'll put the 6, and then I'll just add the 149.566. And so from there, I can see that the race time will eventually be 148.054. So find a space to write that. And I am going to label it minutes. Squish that in there. All right, let's take a look at the next question. So question number 2, the pesticide DDT was widely used in the United States until it was banned in 1972. It does say that DDT is a toxic to a wide range of animals in aquatic life and is suspected to cause cancer in humans. The half-life of DDT is 14 years, and half-life is the amount it takes for the half of the amount of a substance to decay. So science and environmentalists worry about such substances because these hazardous materials continue to be dangerous for many years after their disposal. So if we start with the 200 gram sample, this function that I'm highlighting right now will allow us to figure out how much DDT there is after X amount of years. So this is just more about a calculator thing. Based on this, remember how I did this in chapter 2? If I wrote the equation here, and your decision is to figure out where to put this 5. And I talked about that 5 is in parentheses, so it needs a hug. So where would it rather be, on the left side all alone, or on the right side where there are the other numbers? And so it's going to go on the right side because it wants to be with other numbers. And again, we're going to type this in exactly as you see it. So bringing the calculator back up, let's put it so we can actually see the equation. So it's going to be 200. I do parentheses like they have, type in my number. I hit the exponent button, which is that button right above the division key. And then I'm going to do parentheses again and put in 20 divided by 14 as my fraction. And so when we're done, and with 5 being in there, we get 74.299. So I'm just going to make that 74.3. So what it means is in 5 years, the amount of DDT let's remember that number again, is 74.3. And this is in grams, so I'll just write grams. All right, let's take a look at the next one. So on this one, this is that whole matching thing. So putting what we would think is the best. So when looking at the R value, the correlation coefficient, the goal is to have R equal -1 or 1, depending on if the data represents a negative or positive correlation. So this time what we're going to do is we're going to arrange the letters from a scale of -1 to 1, with 0, that's no correlation, being in between the -1 and 1. So when I look at which is, if I go for my no correlation, that's I think where I'm going to start. That's F. That should be right in the middle. When I look at which one has the best positive correlation, that would be C. So I'm going to put that all the way to the right. And when I look at which one has the best negative correlation, I think that's D. And now everything else is going to go in between. So in between D and F will have to be my other negative ones. And probably the only one that looks negative is B. So that's going to go in here. And then the other two, A and E, look positive. So they're going to go in between F and C. And which one looks best is A. So that'll go closer to C. And then E would just go below it. So I'm putting them in order of their best to worst, and also based on their negative and positive. All right, next question, similar to what was on your showcase of learning. The wholesale price of the used Subaru is given in the table below. So what they did is they ran the regression. You can see your linear and your exponential, and which model is better. I'm going to say the exponential. And again, why? Don't forget to answer that. It's just because the curve hits more points. So now that I've decided on the exponential, I have to write the equation. So I'm going to take A and put it in for A, and B and put it in for B. So it's just, we'll go 3 decimals, Y equals A. And I'm going to go 3 numbers behind the decimal. In parentheses, I'll put B, 3 numbers behind the decimal, rounding to the X power. So now what we're going to do is using the chosen model, what we wrote here, what's the y-intercept? So again, the y-intercept is the number that's more by itself, and that's that 19,705.581. And again, that's always the beginning. And what is y representing in this? It's the beginning. If you look at your table, or not your table, your graph, you can see it's the beginning wholesale price. So if I have to give it a unit of measurement, I'm just going to put a dollar sign with it because it's money. And now using your chosen model, you're going to have to either identify the slope or the growth factor. So since we did exponential, we'll be going for growth factor and rate. And again, the one we want is the rate. And that's where this R comes into play. So my R is the other number, or I'm sorry, my G is the other number, the growth factor. And remember, G comes because they take 1 and they either add or subtract that rate, that percentage. And since I have 0.917 and the data is going down, this is definitely a subtraction. So I'm going to erase this and show you just the subtraction. So if I put the numbers in there, I just have to figure out, if you thought of this as money, how much with the dollar would you spend to get that 92 cents? And you can just go to your calculator and just type that in. And then that's my decimal version. I want the percent version. So one thing I can do is just take it times 100. Or I can move that decimal 2 times to the right. Either way, R, which was 0.083, is actually 8.3%. And again, when I have to explain what it means in context, remember, this is a rate, and so something was going down, and we already talked about it, that the price was going down. So the price of the car, or the value of the car, is decreasing by 8.3%. And how often? Again, they use years, so I'll just say every year. And then we're going to use this chosen model again, and we're going to put in how often or how much a 12-year-old Subaru would be worth. So essentially what's going to happen is where I just wrote that X, I'm going to erase the X and put a 12 in, and then I can just go to my calculator and type it in. So let's move this so you can see it. So clear out some of this. And just always double check your numbers look right when you're typing them in. Again, I'm going to hit that exponent button above the division sign, and I'll put in my 12. And remember, the price is going down. So 12 years old, I should be seeing a Subaru that's not worth that much. And it's worth $6,966 and what was the change? 61 cents if I round. All right, I think this is the last question. So in the showcase of learning, this was about a cup of coffee. Now we're putting a hamburger in the snow. So we grill a hamburger and then we put it out in the snow, and what should happen? Well, the temperature of the burger should be going down. And this time they wrote our two equations. We've got our linear and our exponential, and we're just going to go through and answer the multiple choice. So in the first ones, we're going to be looking at linear. So what's the y-intercept? So again, the y-intercept is this number that's alone. So when I'm looking, I can see just by looking at the numbers in there that this one's out because they don't even have that number in there. And the other thing is the temperature's decreasing. So yeah, so 1 and 3 definitely sound like they're showing up. But it's the y-intercept. So remember, y-intercept is the beginning. So I is the temperature is predicted to decrease. Nope. 3, the temperature of the burger is predicted to decrease. And 4, at the beginning, oh, there's that beginning word, the temperature of the burger is predicted to be this. So it's going to be 4. And then the slope. So the slope is our other number. Whoops, I take it back. I wasn't looking at the right one. And so, sorry, I looked at the wrong one. Let's rewind. So, take it back. This is the number that's by itself. So, it's actually 2. At the beginning of the experiment, the temperature of the burger is predicted to be 174.275. All right, now let's go to the other one. Sorry about that. So, here we're going to look at the slope. And the slope is, remember, something's changing. And in this case, our temperature is decreasing. And this is how fast it's decreasing every minute. So I'm just looking for that. So the temperature is predicted, reading the first one, to decrease by 1 degree every 2.20 minutes. Nope. At the beginning of the experiment, the temperature of the burger is predicted to be, not that one, that's the y-intercept. And in fact, the last one's the y-intercept. So it should be this one. The temperature of the burger is predicted to decrease by that amount every minute. All right, last 2. Now we're going to use the exponential model. And again, what's the y-intercept? Well, this time the y-intercept is that 175 number. So we're looking at the beginning, the temperature's 175. And that's what I notice on option 4. And then again, the growth factor, which really means we want the rate. So G is this number. And to get there, I have to subtract some amount from 1. So I can just go to my calculator and type that in. Now, what's the difference between those numbers? And so I get 0.14, but remember, that's the decimal. If I move that decimal 2 times to the right, it ends up right here. And when I just look at the numbers popping up in the answer, 3 looks like the best. So for each additional minute, the temperature is decreasing by 1.4%. And that's it. I don't see where my off button is, so this might take a moment to figure out where it is. But otherwise, turn this in.